In this video, we will explore the fascinating proof of the Euler characteristic using electrical circuits, focusing on Kirchoff's current law KCL and Kirchoff's voltage law KVL. There are many straightforward proofs of the Euler characteristic, but I recently found an intriguing proof in Professor Pedro Vieira's lecture using electrical circuits. I have included a link to his lecture in the description along with other references I found online about this particular proof. Be sure to check them out. Let's get to the proof. Imagine we have a graph that can be drawn on a sphere like a cube or any other planar shape. Our goal is to understand why the Euler characteristic chi equals to v plus f minus e, where v is the number of vertices, f is the number of faces, e is the number of edges, remains constant at 2 for such graphs. To grasp this concept visually, think of constructing the graph using metal wires. Now start by injecting an electric current I at one vertex. Remove an equal current I at another vertex. So this setup helps us visualize how current flows through the graph. Now the current will flow through the graph from the injection point to the removal point. We need to determine the current flowing through each edge of the graph. Let E be the number of edges which are our variables. Now we will count equations. For that we need Kirchoff's current law KCL and Kirchoff's voltage law KVL. So Kirchoff's current law is that conservation of current at each vertex. So at each vertex the total incoming currents equal the total outgoing current. This gives us V minus 1 equations, because if we impose conservation at all vertices except one, the last one will automatically satisfy the conservation. So now the Kirchhoff's voltage law, which is the total potential going around phases. For each phase, the total potential difference around the loop must be 0. That is, delta V potential equals to 0. This condition ensures there are no holes in the graph. So this gives us f minus 1 equation. Here it is sufficient to impose 0 potential inside and automatically the outside will be true. So see that figure. So here we have two faces, one is inside, one is outside, but the elementary loops equals to 1. So if there is 0 potential from inside, then the outside is also accounted for. So therefore we have f minus 1 equations, as the very last phase potential is determined automatically. So now the Kirchoff's current law KCL gives V minus 1 equations and Kirchoff's voltage law KVL gives f minus 1 equations, and the number of variables H representing the edge currents equals to the total number of equations from Kirchoff's current law and Kirchoff's voltage law. So the number of variables, which is the edge currents, number of edge currents, which is E, equals to V minus 1 plus f minus 1. So therefore V plus f minus E equals to 2. So now you can generalize it to higher genus surfaces. When considering a graph drawn on a surface with genus G, we must consider additional constraints. Specifically, the potential difference around each of the new cycles found on the surface must be 0. Each increase in genus introduces 2 additional independent cycles, each imposing a condition of 0 potential difference. Therefore, for a surface with genus G, there are 2G additional conditions to satisfy. So the Euler characteristic chi for a surface of genus G is given by chi equals to 2 minus 2z. The genus G represents the minimum genus of a surface where the graph can be drawn without edges crossing. For example, a planar graph can be drawn on a sphere genus 0 surface, while a graph requiring a torus, a donut-shaped object, has a genus of 1. So now we'll consider some examples. So first consider the cube. We will calculate the Euler characteristic by V plus f minus E. So the number of vertices V equals to 8, number of faces equals to 6, and the number of edges equals to 12. So the chi equals to 2 for the cube. So now we make a square at the top and bottom and make a genus 1 surface cube with a hole in the middle. So the number of vertices equals to 16, number of faces equals to 10, and the number of edges equals to 24. So V plus f minus E equals to 2. So note that here each face is not contractible. So now we consider another example. And here we make each face contractible. So here the number of vertices equals to 16 and the number of faces is also 16 and the number of edges is 32, which is that 24 plus 8 extra edges. So here V plus f minus E equals to 0. So here you see that each face is contractible. In the previous example, which is not. The theorem states that for the faces loops in a graph, they must be contractible, meaning they cannot contain holes. To ensure the theorem applies, we need to adjust our shape so that every face becomes contractible. So if we don't include these edges in the figure, we essentially have two separate graphs, the outer cube and the inner cube. So this means that if we inject current into the outer cube, it won't affect the inner cube. To ensure the current flows through both, we need to inject it into the inner cube as well. This is analogous to computing two planar graphs separately. Therefore, we can state that every edge should be connected and we cannot have disconnected components. So now let us begin by drawing a parallel between the circuits and polyhedra as illustrated in the figure. So place a sphere above the planar circuit diagrams and connect each node to the north pole with a line segment. This is called stereographic projection. The vertices are defined as the points where these segments intersect the sphere, resulting in a convex polyhedron. So convex polyhedron, meaning that a polyhedron is a three-dimensional shape formed by connecting multiple polygons, and a polyhedron is considered convex if every line segment connecting any 2 points within it lies entirely within the polyhedron's interior. So otherwise a polyhedron is said to be concave. So any convex polyhedron surface has Euler characteristic chi equals to V plus A minus E equals to 2. So now it is evident that the number of vertices of the polyhedron corresponds to the number of nodes of the circuit and the number of edges corresponds to the number of branches of the circuit. However, the number of faces F of the polyhedron is equal to the number of elementary loops plus 1 in the circuit because the topmost face represents the open area surrounding the circuit. So Euler's polyhedron formula relates to the Euler characteristics of the sphere and applies universally to the spherical polyhedra. Now we give an illustration demonstrating the formula for all Platonic polyhedra, meaning tetrahedron, hexahedron or cube, octahedron, dodecahedron and isosahedron.